All right, so in this chapter, we're going to be talking a lot about what's called exponential functions, which is a new type of function, and we're going to talk about their graphs mainly today, but we'll get into like what situations represent an exponential function, because you can have some that go up and some that go down, just kind of depending on what the equation looks like or what the situation is talking about. And then we'll also talk about logarithms and how to use those and evaluate with them, but that'll be towards like the middle to end of the chapter. Today we're just going to start with talking about exponential functions, what they look like, how to graph them, some of the basics about them. So they look like this form, y equals b raised to the x power. So you're going to have an exponent. That's why they're called exponential. It kind of has that word exponent in it. And so we're going to be looking at a number, which in this general equation, b represents the base, which would be the number that you're raising to the power. So that's like a 2 or a 3, or it could be like a 1.5, or even a fraction like 1/2 or something like that. So you're raising that number to some exponent. So you're squaring it, you're raising it to the third power, to the fourth power, so on. So a couple examples they have down here are y equals 2 to the x power, f of x equals 4 to the x power. Remember, f of x and y mean the same thing. Okay, f of x is just function notation when you're talking about a function, but you can always replace it with y, especially when you're making graphs and you're trying to figure out which one is your x and your y coordinate when you're going to the coordinate plane. Okay, now these two down here, these are not, okay, keyword here, not exponential functions. This y equals 4x, this would just be linear. That's just a straight line. Okay, when it was x to the fourth power, that's what we were just dealing with in the previous chapter, because that would be like a polynomial type equation. That would be a quartic function. Okay, so that graph would like curve a couple times as it's going through the graph. Exponential functions don't look like that. Notice how this one had x as the base and 4 as the exponent. You want the exponent to be where your variable is at in order for it to be an exponential function. Okay, so let's take a look at an example here. We're going to graph the function f of x equals 2x, or 2, raised to the x power. So you guys should have a graph in your packet there for you. Now notice how like it goes up really tall, like I think yours goes up to 20. That's because when you're raising something to a power, you're taking it times itself. So it's going to start to grow really fast. That's what exponential functions do. They grow really quickly. So when I'm going to create like my XY chart here, so you're going to want to make t-tables for all of these, where you put x on one side, y on the other side. And we're going to put numbers in for x, okay? So I'm going to start at -2, and I'm going to go up to +4. So what I do then is I take all of those numbers and I put it in for that exponent. So if you guys have calculators, you're going to take 2 and then raise it to the -2, raise it to the -1, raise it to the 0 power. And when you do this, you're going to get decimals for some of them, and that's fine. I would probably write it as a decimal just because it's going to graph easier. It's hard to graph fractions because you have to know like what that fraction represents on the graph. Okay, so if I take -2 and I raise it to the -2 power, I get -0.25. Okay, and if you have a calculator, I would suggest that you guys try typing these out so that you can make sure that you're getting the right answers as me. Oh, you're right. It is positive because it's 2 raised to the -2. Thank you. Okay, now let's do 2 raised to the -1. That would be 0.5. What do you get when you take 2 to the 0 power? Not 0, 1. Anything to the 0 power is always 1. Okay, now 2 to the first power would be a 2. What's 2 squared? 4. 2 to the third. And the last one, 2 to the fourth. 16. Okay, so those are all of our points. notice how they're starting to grow. Like if I did 2 to the 5th power, that would jump up to 32, which I don't have room on my graph to do that one. So now you guys are going to graph it. So -2, for these first couple, we'll have to estimate where they are. Okay, so -2, you're going up 0.25. For -1, you're going up 0.5, which would be halfway between 0 and 1. Now at 0, I'm up at 1. At 1, I'm at 2. 2, I'm at 4. 3 is at 8. And last one, 4 is at 16. Mine's going to be way up here. Okay, yours should fit a little bit better on your guys' paper. Mine's going to start to go off. But you can kind of start to see the general trend is that the farther I go to the right on my x-axis, the more quickly it's going to shoot up. My y values are going to start to get really big really fast. That's what happens with these exponential functions. Okay, so to graph this, it's going to be kind of a curved shape. And you're just going to go all the way up through those points and just kind of show that it's going up. Now, as it comes down here, it's going to gradually get closer and closer and closer and closer to that y-axis, but it's never going to cross the y-axis. You're always going to get numbers smaller and smaller and smaller and smaller, but you're never going to see it become negative or equal 0. Okay, it's always going to stay positive, and it's going to be right above that. So we just have the line ride as close as we can to that y-axis without actually crossing it. So on the bottom of that page, you guys should see this little piece. This just kind of tells you what makes something growth or decay. Like, what's the difference? How do you know if it's going to shoot up like that one just did, or if it's going to go the other direction, so it's going to start up and then it's going to come down and go low. Looking at your kind of your base will tell you whether it's going to be growth or decay. If your base is greater than 1, like my problem had a 2, it was 2 raised to the x. If your base, your constant, is more than 1, so if it's 1.5 or 2 or 3 or 3.5, it's going to be a growth function. If that number is in between 0 and 1, so if it's 0.25 or if it's 1/4 or 1/3, those are all going to be decay. So you can look at that number just by to kind of give yourself like an idea of what this graph is going to look like before you start plotting points to know if it's going to go up or if it's going to go down over time. Okay, so let's go to the next page. So they want you to graph this, and they also want you to say whether it's showing growth or decay. This one looks a little different than our last one because they've got a 10 sitting in front of the number raised to the exponent. Okay, but that's not going to change anything as far as evaluating. You're still only taking that 3/4 to the x power. I just want to get this started with you guys. Okay, I'm going to go ahead and still start at -2. I'm just going to go up to +2 for this one. For yourself, when you're doing these, you can kind of choose how many points you want to add. I would say you're going to want to do like 4 or 5 points just to make sure that you've got a good spread of the graph. So be careful when you're entering this one in on your calculators. Okay, you want to do that 3/4. That's the only thing that's raised to the -2 power and the -1 power and the 0 power. So if you want to do that first and then take it times 10, if you're not going to do like one sentence, that's what I would do. Now, if you're going to do one complete sentence on your calculator, make sure that you put that 3/4 in parentheses then. Okay, so 10 and then parentheses your 3/4, and that's going to be raised to the -2. Okay, and so I'm getting positive 17.8 if I round it. Okay, now you're going to get like a really weird decimal. Mine's 17, and it's 7 repeating, 17.7 repeating, but I'm just rounding it to 17.8. Okay, now I'm going to do it again. I'm going to take 3/4, raise it to the -1 power, and then take it times 10. I get 13.3 repeating, so I'm going to round that to 13.3. Are you guys getting those numbers out there as you're testing them? So I want you guys to try to finish filling out this chart, and then I want you guys to graph it. After those decimals, you have to just kind of roughly guess where you take your end. Okay. Yes. Yeah, so it's kind of like the backwards of what we just saw. The last one is going down this way, this one's graphically down this way, so it would eventually flat line of that. All right, so for the next couple of points, for at 0, you should have had 10. 1 is 7.5, and 2 is 5.6. Again, that last one I rounded. And then we go and we graph. So let's see, I might have to go out just a little bit more. So that first one is at -2, 17.8. So way up there. -1 is at 13.3. So let's see here. Just a little above 13. 0 is at 10. 1 is at 7.5. And your last one, 2 is at 5.6. Now you could add more points if you want, but you should start to kind of see that this one is going in the opposite direction that that first one did. So it's coming down and it's going to the right. Now eventually this graph, if I kept following it, it's going to have the same trend that my other one did, where as it gets closer and closer to that y-axis, it's just going to gradually kind of flat line out. It's not going to cross the y-axis. It's just going to get really, 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 really close. It's going to try to get as close to it as it possibly can. Now, looking at this graph, the last one was an exponential growth because it was a whole number of 2. So this one's going to be a decay function. Can you guys tell me why? What about the actual function makes this a decay function? Good, it says 3/4. This piece right here that's raised to that exponent is in between 0 and 1 because it's 0.75. So that's what makes it a decay. That means that it's gradually going down over time. Okay, you guys try to do number 2 Try to do the whole thing, make your table and graph it, and then decide if you think it's a growth or a decay function. So I'm going to use the same points that I used on the last problem. So I'm going to go -2 to +2. For that first one, and I rounded all of my answers here, I got 1.8, then 1.9, 2, 2.1, 2.2. Now all my numbers here are really small. Okay, so when you guys graphed it, it's kind of hard to even see just from the graph like what it's going to do long term because it's such a small amount of space that if I had a graphing calculator to like type this into, eventually, like if I, especially on your calculators, you can kind of zoom in and zoom out to see more of the function. You'll see that this does start to grow, but it just takes a long time for it to do that. It's a little bit more gradual. Because they're so close together. Okay, so if it helps you, you could always go and add more points if you weren't sure what's happening. But I'm starting to see, like, it is slowly going up. Okay, so on the right side, it's going to eventually start to shoot up. And down here on the left side, as it goes more to the left, it's going to start to get closer and closer to the y-axis. Okay, so did you guys say this was growth or decay? Growth. And again, if you look at that number that's raised to the exponent, that 1.05, that's bigger than 1. Just barely, but it is bigger than 1. And so that's what makes it become a growth function. So on the next page, all exponential growth functions and decay functions kind of have the same shape to them. Okay, so all growth functions are going to go up over time. And like I said, the left side is going to get really close to the y-axis. And all of your exponential decay functions are going to look the same, but they're going to be reversed. Okay, so they go the opposite direction. So places that we see exponential growth and decay happening outside of just putting numbers in our calculators and graphing them. I'm talking about real life type stuff here. Okay, this happens a lot when you're dealing with money. Okay, when you're investing money. In the future, when you guys have jobs and careers and families, you're going to be talking about where are we going to put our money? How are we going to invest in our future so that I don't have to work for the rest of my life, so that I can retire someday? So you're going to have to think about what is like the best place for me to put my money? Where am I going to see it grow the most? Okay, because we want our money to grow. We don't want it to decay. because then that means that we lose money. But companies have to look at that stuff all the time, especially companies that are like putting out new products. They have to watch what's happening so that they're not going bankrupt over time. They want to make sure that they're making money. So that's when we start getting into some of these models that are represented by this formula. And it says A, capital A, and then parentheses T. So that's kind of your function notation again. That's like where your Y would be on a graph. Equals little a times 1 plus or minus r raised to the t. So I'm going to talk to you guys about what all these letters mean when we're dealing with an equation like this. So first of all, little a. Let's talk about that one first. Okay, little a is talking about the initial amount. So this would be like if you were looking at investing money into some kind of fund or some kind of account that's going to, over time, generate you more money. That would be the amount that you put in at the start. So like you're going to put in $10,000. Okay? Now, the R, the little r here, represents the rate of increase or decrease as a decimal. So rate of increase or decrease as a decimal. So increase would be if you have to pay interest on something, or if you're making money back, like if it's compounding for you and your whatever money you have in the account, you accrue interest on it like yearly or like quarterly or something like that. Decrease would happen if you're talking about something losing value over time. Cars is a really good example. The second you buy a car and you start to drive it, it starts to lose its value because you're putting miles on the car. You're more prone to like crashing it and those kind of things that depreciate the value of the car. T stands for the number of time periods. Most of the time we talk about this in years. So if you're looking at something depreciating over 5 years or 10 years. So at the very front here, where it says capital A, parentheses T, that's like the final amount after you do all the math. So that's what you're left with. That's how much you've made, that's how much you've lost, depending on if it's a growth or decay type function. So we're going to do just a couple of examples here using this equation. Okay, now you're probably going to be only putting stuff into the right-hand side because that's what they're going to give you information for. And what you're trying to find is the final amount for these types of problems. Okay, so for this first one, it says that Dale invests $5,000 in an account that pays 6.25 interest per year. How much will be in the account after 5 years? Now this is assuming that he's not putting any more money in the account. He puts $5,000 in there, he lets it sit for 5 years. He doesn't touch it, he doesn't add anything to it. So A is the initial amount, little a. So if it helps you, I would maybe write this out. Like little a is going to be that $5,000. What is the 6.25% going to be? R. Okay, now we need to write this as a decimal. How do I change percents to decimals? Not times. Divide by 100. Okay, so you're going to take 6.25 and divide by 100. Now it says that it pays that much. That means that it's a positive increase here of money returned. So it's not going to be negative. It's going to be a positive decimal. So it's going to be 0.0625. If it had said he was losing money, then we would want to use a negative decimal instead. Okay, and then T would be how much? Good, 5. Okay, so let's go ahead and plug this in. We're going to take 5,000 times, in parentheses, 1 plus that 0.0625, and all of that's going to be raised to the 5th power. Okay, so I'm just going to split this up a little bit. I'm going to do 1 plus that 0.0625, raise that to the 5th power, and then take that times 5,000. Okay, so this is in money, and I am getting $6,770. And then for my cents, it says 0.405. So how should I round that? 41. 41 cents. So this is how much would be sitting in that account. So if we took this and we subtracted 5,000, he made $1,770.41 by that money just sitting in that account, not doing anything to it. Okay, so there's one more on this page on the bottom. Now, be careful with this one. Key word here is that this city is losing population. So I want you guys to read through it, identify what your A, your R, and your T is, and then do the prediction for this city with its population. All right, so can you guys tell me what little a is for this problem? Good. What's our rate? Good, 0.03. Now I'm going to go ahead and write a negative 0.03 because they are losing people over time. And how much time are we looking at? 10 years. So I would have typed it in my calculator like 7,500 times 1 minus that 0.03 raised to the 10th power. Now we're talking about people here, okay? So you got to be careful with rounding. You can't have a portion of a person in a town. Okay, we're not going to go there. I'm saying you can't have a portion of a person in a town, okay? So when you round, you have to be careful. What'd you guys get for an answer? $5,530, and that would be residents or people, however you want to label that.